Most modern web applications operate as rigid state machines. They present a fixed layout and wait passively for instructions. The underlying software logic only registers a change in state when it receives an explicit Boolean input from the user, a mouse click, a keyboard stroke, or a form submission. When experiencing high cognitive load, an operator's cursor moves erratically across the complex interface. Detecting this hesitation, the system proactively flattens harsh grid lines into a dark, uniform aesthetic. The primary node then emits a repeating radial pulse, pulling focus to the next logical step. Standard error handling requires the user to make a mistake first, which then generates a reactive text warning. This system operates proactively, physically guiding the operator before an error occurs. Web interfaces do not have to be passive grids waiting for commands. They can be engineered as active environments that physically adapt in real time to mitigate operator fatigue. Achieving this requires a strict engineering problem. An application must process massive media files and continuously calculate behavioral adaptations simultaneously, all without introducing severe network latency. The solution is a framework called the Neuro-Symbolic Engine, which completely eliminates external cloud dependencies from the workflow. The first pillar of this framework is behavioral telemetry. Instead of logging discrete clicks, custom sensors continuously track the user's physical micro-interactions. The second pillar relies on client-side machine learning models to autonomously analyze and edit media directly on the local machine. The third pillar is the execution core, which forces heavy media rendering to happen natively within the browser environment itself. Together, these three pillars form a completely serverless, edge-side architecture. Moving both computation and inference directly to the client edge eliminates the network as a bottleneck. This architecture secures data within the local network while maintaining the processing speed of a native desktop application. To understand how the interface anticipates the user's needs, we have to look at the invisible data pipelines driving those physical transformations. This X-ray view shows the active geometric mesh overlaying the layout. Custom React hooks continuously capture the cursor's precise velocity vectors, measuring distance over time to determine exactly how fast and erratically the mouse is moving. The system also tracks input dwell times. If the cursor hovers over a complex control without triggering a click, a timer logs those exact milliseconds of hesitation. Secondary sensors capture timeline scrubbing precision and track rapid, repeated play and pause toggles. All of these continuous telemetry streams are fed directly into a central state manager called the Global AI Kernel Context. Unlike standard state management that simply holds static variables, the AI kernel operates as an active monitoring layer, constantly evaluating incoming behavioral metrics. Within the AI kernel, the vector and timer data streams flow into a parsing engine known as the Edge Memory Matrix. This matrix filters the raw information into distinct output channels, representing the user's current status. By evaluating these inputs, the matrix calculates the difference between a user executing a rapid, confident crop and an operator agonizing over a control panel. When the friction calculation exceeds a specific threshold, the matrix sends a command to the Framer Motion library to physically flatten the animations and initiate the guiding pulse on the primary interface. Structural telemetry transforms subtle physical movements into data points. By correlating erratic cursor paths and dwell times with failed interactions, the system creates a quantifiable profile of user friction. Pacing quickens slightly. That same level of intelligence is applied directly to the media processing timeline itself. The application integrates pre-trained MobileNet models using TensorFlow.js, running entirely within the client environment. To automate editing tasks, the pipeline must first perform scene detection by extracting raw video frames at specifically calculated intervals. This animation illustrates how the system converts visual frame data into multi-dimensional arrays. A single two-dimensional video frame is expanded into a layered, three-dimensional grid of numerical values, known as a mathematical tensor. The AI evaluates the footage by running a comparative logic check on these arrays. It performs a mathematical subtraction between two consecutive tensors, Tn and Tn-1, resulting in a single new grid that represents the absolute difference, or the delta. If that calculated delta exceeds a specific mathematical threshold, the system reliably flags a major camera cut or a significant shift in on-screen action. Once a scene change is mathematically confirmed, the system immediately triggers an automated workflow. The AI autonomously constructs a set of instructions to remove dead air from the timeline and apply necessary transitions, all without requiring any human input. Every piece of this complex tensor math occurs natively within the browser, strictly avoiding round-trip requests to external AI APIs. Executing autonomous inference entirely on the local machine severs the dependency on third-party computational services. Media workflows become highly secure and significantly faster. The ultimate bottleneck for any web-based media application is the execution of the final high-resolution video render. This flowchart demonstrates the traditional high-latency rendering loop. Massive data blocks are forced through a narrow upload funnel to a remote cloud server, held in a processing queue, and eventually downloaded back to the user. To resolve this bottleneck, the application utilizes a specific compiled environment known as WebAssembly, or WASM. The engineers ported the industry-standard C-based FFmpeg library directly into WebAssembly, allowing it to execute locally. Bypassing the network entirely alters the traditional data pipeline. Raw 4K media files drop instantly into the local browser's RAM, completing a tight, highly efficient execution loop. This creates a zero upload advantage. Gigabytes of raw video can be fully processed without consuming a single byte of outbound network bandwidth. For enterprise environments, the benefit is absolute data privacy. Sensitive corporate intellectual property never leaves the local machine. The local core also powers a professional utility layer, utilizing a Fabric.js spatial canvas for precise drag-and-drop watermark and branding overlays. The WebAssembly environment handles multi-format extractions as well, generating MP3 tracks or high-quality GIFs natively on the device. Compiling foundational rendering libraries into WebAssembly breaks the final tie to cloud dependency. The local browser operates entirely as an independent, high-performance workstation. Pulling back to a macro-level view allows us to see how these isolated components function together. This stack's foundation is the WebAssembly compute core, securing zero-latency local rendering. The TensorFlow inference layer slots on top, automating complex tasks. Finally, the AI kernel telemetry layer completes the stack, mitigating cognitive friction. A unified boundary safely encompasses this isolated client. Web applications no longer have to be built as static, reactive layouts. The transition towards systems that anticipate user hesitation represents a shift toward more empathetic, human-centric software design. The combination of local machine learning, rapid edge-side execution, and continuous behavioral telemetry provides a path for building high-performance web tools that do not compromise on security or responsiveness.